All digital models, including all stochastic digital models, can be classified as either finite impulse response models or infinite impulse response models. As the name says, these alternatives concern the impulse response of a system. So, at the input of a system, we will consider an impulse. Remember that the impulse is a signal which is zero everywhere, save at time instant t equal to 0. Our signals here are discrete in time, so they only exist at sampling instants, which are those time instants multiple of the sampling time. If we consider the integral of this signal using the rectangular rule, then the integral of a signal like this, an impulse, will be the area of this rectangle. We will consider that the amplitude of this impulse, here at time t equal to 0, is 1 divided by ts. In this way, the integral of this signal will be equal to 1, which is the area of this rectangle. So, a finite impulse response system is a system with an impulse response such that after some time the response becomes 0. It may take longer or shorter, but after a while, at all sampling instants, the impulse response is 0. That is why we say that it is finite, because it will be different from 0 only for a finite period of time. Of course, all finite impulse response systems are stable. Remember that it is the convolution of the impulse response with an input that gives us the output of the system for that input. Now, if this impulse response becomes 0 after a while, this convolution with any bounded input will result in a bounded output. On the other hand, an infinite impulse response system is a system with an impulse response that never becomes 0. Of course, some infinite impulse response systems are stable. Think about a system like this. The impulse response does tend to 0, but only asymptotically. There is no period of time after which the response always becomes 0. Still, this system with this response is stable because its impulse response tends to 0. Of course, every unstable system will have an infinite impulse response. Response, for instance, like this, which goes to infinity, either increasing or decreasing or oscillating. It doesn't matter. Let us see some examples of finite impulse response and infinite impulse response systems. Think about the moving average. A moving average model is a model in which the output is a moving average of the input. Suppose, for instance, that it is a model like this. In this case, we have a moving average of order 2. It doesn't matter the order of the model. If E of k is an impulse, of course, we usually presume that this input, being an error, being an unknown input, is normally distributed, but presuming that it is an impulse, Well then, after 2 sample times, the output will be 0. Think about it. If E of k is equal to this, then at any time instance sufficiently far from 0, this will be 0. So will this, and so will this. And consequently, yk is equal to 0 for every k larger than 2, which is the order of this moving average. Should we have a moving average of order, say, 100, still, after 100 time samples, the response would be 0. Consequently, the moving average is an example, not the only one, but a typical example of a finite impulse response model. On the other hand, an autoregressive model is a good example of an infinite impulse response model. Let us consider an autoregressive model of order 2, though of course this is true whatever the order of the autoregressive model we are considering. Suppose, for instance, that the output is given by the sum of this input with the following terms. This model, as we can see finding its poles, is stable. If this input here, which we normally presume to be normally distributed, is instead an impulse, we can see that the output of this stable model does not become 0 after a while. Let us create the corresponding transfer function. The sampling time is completely irrelevant, so I will put here a sampling time equal to 1. Here we have our response, and we can see that even though the system is stable and thus its response tends to 0, the response becomes very, very small, but is never equal to 0. Small as it may get, it is always different from 0. The farther I get, the smaller it is, but never 0. That is why this system here, which is autoregressive, is an example of an infinite impulse response system. What I meant a moment ago with the sampling time being irrelevant is this. The response will, of course, be faster or slower depending on the sample time, but its shape is always the same. Here we have 2 seconds of simulation. A moment ago we had 20 seconds, but the shape is the same, and if I put here 10 seconds, we'll still have the same response, save that it now takes 10 times more. Stability or instability are not affected by the sample time, provided that the poles are the same. And of course, if a system has a finite impulse response or an infinite impulse response, that too will also not change with the sample time.